the charge. See, this unit can be a nanocoulomb or a microcoulomb or a coulomb or whatever, but each line of flux corresponds to 1 unit of a charge. So if there are q units of the charge, then how many lines of flux will emerge from this? Then there will be q lines of flux that emerge from the surface. Right? So the electric flux linkage can be understood here as the number of lines of flux that are emerging from this surface. Right? So in the examination he may say there is a surface S with 10 units of the charge, and then he may ask you to find out the number of lines of flux that theoretically that can emerge from this surface. Then what will be the answer? That will be 10 lines of flux that emerge from the surface. Or he may give you some figure like this, and then he may ask you to find out what is the total charge present in this surface. So you have to count the number of lines of flux and then give the answer Q as the number of lines of flux in terms of units. So far there is no question in this concept, but you can expect such type of simple 1 mark question in the examination. Okay, so now we can state Gauss law as the total displacement or electric flux. I told you the other way to define electric flux is in terms of displacement. Both of them are same, right? So either you call it as a displacement or electric flux. The total displacement or electric flux linking a closed surface S surrounded by an electric charge Q is equal to the amount of charge enclosed with surface. So surface integral d dot ds is equal to Q. If this charge Q is uniformly distributed across the surface having a volume charge density rho v. What is rho v? It is charge per unit volume. Say this charge is uniformly distributed with a volume charge density rho v. Then can I write Q as volume integral rho v dv? Volume integral rho v dv. This is called Gauss law in point form. Very important. Gauss law in point form. Sorry, this is called Gauss law in integral form, not point form. This is called Gauss law in integral form. This is surface integral and volume integral. Which theorem you need to apply? Apply Gauss divergence theorem. When you apply Gauss divergence theorem, we know surface integral gets converted to volume integral. So triple integral. This is volume integral of del dot d dv is equal to volume integral of rho v dv. So the same volume in both LHS and RHS. So you get del dot d is equal to rho v. So this is Gauss law in point form. This is Gauss law in point form. So you can represent Gauss law in integral form or point form. Now, for isotropic materials, how do you represent Gauss law? I told you this is an important 1 mark question. The difference between isotropic and anisotropic materials is isotropic material is that material in which the properties of the medium do not change from direction to direction. In anisotropic materials, the properties of the material change from direction to direction, or in simple way, epsilon is constant for isotropic materials. And for anisotropic materials, epsilon is not constant. You can play with epsilon and d is equal to epsilon e only for isotropic materials. So Gauss law for isotropic materials would be Gauss law representation for isotropic materials would be, let's take the case of isotropic. Isotropic materials would be surface integral E dot ds is equal to Q by epsilon, or del dot E is equal to rho v by epsilon. You can play with epsilon only if it is a isotropic medium. For an isotropic medium, or anisotropic medium or anisotropic material, just write d is equal to epsilon E. Surface integral epsilon E dot ds is equal to q, or del dot epsilon E is equal to rho v. That's all. Do not play with epsilon, because for anisotropic material epsilon is not constant. Important 2-mark question, frequently asked in IES in other PSU exams. The question would be something like this: which of the following equations represent Gauss law for anisotropic materials? First option may be del dot E is equal to rho v by epsilon, and last option may be something like del dot epsilon E is equal to rho v. Don't jump and put the option, select this option A, thinking that this is the Gauss law. This is Gauss law, correct, but this is not the representation for anisotropic materials. It is a representation for isotropic materials. So carefully select the option which is valid for anisotropic material, or if the question is for isotropic material, choose the appropriate option. If the material is not given, then take it as isotropic material. The next topic that we are going to discuss is electric potential V. Electric potential V. Having understood electric field and electric force, which we know that they are equivalent to each other or similar to each other, let's see what is this potential. Before we understand what electric potential is, I want you to understand the work done. When do you say work is done? It can be work done on the body, or work done by the body, or work done on the system, or work done by the system. If a body that is being experienced by a force is moved from one point to another point, then work is said to be done. Right? That means if the force causes displacement, this is the definition from physics. If the force causes displacement, then we say work is said to be done. Right? If you consider the case of fields, there is a positive charge. Say there is a charge Q, and in the vicinity of this charge there is some field present, right? Now there is one more charge, say Q1. If there is a positive charge in the vicinity of this charge Q, there would be a repulsive force between these two charges. If there is a negative charge, then there will be attractive force between the charges, right? Whatever be the case, if the force causes the displacement, if a body that is being experienced by a force is moved from one point to another point, then we say that work is said to be done, right? So it can be attractive force or repulsive force. Whatever be the case, if it causes displacement, then work is said to be done. And we know the work is associated with energy, and energy is of two types. Energy can be kinetic energy or potential energy, right? So it is kinetic energy or potential energy. Whether it is kinetic or potential, energy is always a scalar quantity. It is measured in terms of joules, right? Now if we come back to these fields, so any field that you consider whose source is electric charge Q, in the vicinity of this charge Q, if there is some other charge present, this leads to attractive force or repulsive force between these charges, and there is certain amount of displacement associated due to this force, right? And we know that displacement will result in work done, and work done is associated with energy. That means every field can be associated with some energy. Now coming back to the field again, if I consider a field, please concentrate on the definition. If I consider one particular field, what I'm trying to say is, if in some field, if there is no mechanism by which the energy represented by this work done can be dissipated or absorbed, I repeat, I consider a field in which if the energy represented by the work done in this field can neither be dissipated nor absorbed. What do you understand by this statement? So when you say work is done by the system, then there is some amount of energy dissipation. If the work is done on the system, then there is some amount of energy that is absorbed by the system, right? So it all depends on whether it is a work done on the system or by the system. So the energy can either be dissipated or absorbed. And we know that any field that you consider, there is certain amount of energy associated with this field. So this could be energy dissipation or energy absorption, right? So I am going to consider one particular field, and I am trying to understand the properties of this field. In a field, okay, in this field that I considered, if there is no mechanism, by which the energy represented by the work done, in this field can be dissipated or absorbed. What do you understand by this statement? No mechanism means what? That means you are considering a field in which there is neither energy dissipation nor energy absorption. Okay? So if there is neither energy dissipation nor energy absorption, then what happens to the energy? The energy is conserved in this field. So I'm considering a field where the energy is not changing, where the energy is conserved. So this kind of field is referred to as conservative field. This is referred to as conservative field. Conservative field is a field in which energy is neither dissipated nor absorbed. Okay? Mostly we refer it to the dissipation of energy, not the absorption of energy, because usually it is a work done by the field, or so it is energy dissipation from the field that usually occurs. So conservative field is a field in which there is no mechanism by which the energy represented by the work done in this field can be dissipated. Means energy cannot be dissipated in this kind of field. If the energy is not dissipated in this kind of field, then it is referred to as conservative field. Why are we more interested in conservative field? Because electrostatic field is an example of conservative field. Very important, one more question. Electrostatic field is an example of conservative field. So whatever static electric field that we are discussing, that is nothing but a conservative field. That means you need to remember that there will not be any energy dissipation associated with this field. So the energy would be conserved in this field. Unlike the real fields that we will discuss in Maxwell's equations, they are all non-conservative fields. That means if you take a real field, then there is a certain amount of energy that is dissipated. So energy transformation takes place. One kind of energy gets transferred into the other kind of energy. But here, for static electric field case, there is no energy dissipation. That means there is no energy transfer. We will come back to this electrostatic field in few minutes, and when we will see more properties about electrostatic field, and also how to understand the properties of the electrostatic field in terms of the mathematical models. Now the topic states electric potential V, right? Now how do you define electric potential V due to a charge